We've got another type of differential equation we want to talk about, and it's, as I have up here, linear differential equation. And just like the name suggests here, it involves sort of like a linear equation, but differential involved too. We got a derivative involved. And this is how they write the just basic form of a linear differential equation. So we've got the differential and the y combined in one equation. But to be a linear differential equation, yeah, it needs to be in this form. And I guess the linear part of it, you got y to the first and a first order differential equation because you just have the first derivative. So you can't have anything above first derivative and then y to the first power. Now, the p of x and q of x, that's expressions of x, and those can be, you know, squared, cubes, square roots, things like that. The p of x and q of x here, and you'll see some. We'll do several examples here, but linear differential equation, y to the first and y prime, and then to put it in this form, that's our first thing we'll talk about, that this is what it needs to look like. And so just an example here, y prime plus 3x squared y equals e to the x is a linear differential equation. And in this case, we've got the p of x is 3x squared, and then the q of x is e to the x. But we do have y prime, y to the first. Like I said, the p of x, it doesn't have to be linear. It can be x squared, and then in this case it's an exponential, so you know it's pretty wide open on those. But y to the first, y prime, and then we want those on the same side as well. So now on this one, looks fairly obviously to be a linear differential equation. However, it is not in the standard form that we want, because why? Why is that one not in the proper form? You got an x here. Yeah, you want to be in the standard form of a linear differential equation. You need that y prime by itself, if you will, or coefficient 1, I guess is a better way to put it. So let's put this in the standard linear differential equation form. And so, yeah, this one's fairly simple. Just since I need that to be 1, I'm just going to divide by the x, and so that'll make that one y prime. Of course, this will be y divided by x, but let's write it as 1 over x y times y, and then over here we'll have equal to 2. And so there's our p of x and our q of x. A little different p of x and q of x, but they are what they are. But that's in the proper form, if you will, with the proper form that we will need it to be in. Is that okay? Here's another one. All right, so say we got y prime minus y equals 2xy, which again looks fairly linear there, I guess you might say, but the problem is we got a y over here, and for q of x on this side, you don't want any y's on this side, and so if you've got a y on this side, you got to take care of that. Now, it's the process here to put it in the standard form. Yeah, won't divide by y because that would put a y with that. Divide by y. So basically, it's what I need the y on this. Y is on the same side, so y prime minus y minus 2xy minus 2xy both sides. Make that side 0, and that'll be okay to have 0 on that side. Then we can factor off the y here. let's do this. Just to make it really obvious, let's just factor off of y, make it just plus y here, and then that'll make it a -1 minus 2x. And so now we have it in the standard form. This is the p of x, and then that's our q of x. So, just an example of one not in standard form, that, or not in linear, not a linear. So is that one linear? And like I said, the answer is no here, because no way around it. I've got a y squared, and yeah, you can have x's squared and different things for x's, but for y's, you need a y prime, you need a y. You can't have a y squared. You can't have a second derivative of y, anything like that. So yeah, not so much, okay? You got a y squared, that's going to take it out of the realm of the linear. And, you know, that's for later discussion in a different course. Right now we're just doing linear differential equations. Okay. So, what's the process then? The next question. How do I solve these linear differential equations? Pick that up. Next here. Well, it turns out we're going to need, one way to do it is we're going to use this integrating factor, they call it. So again, for y prime plus p of x times y equals q of x, we're going to need what's called the integrating factor. So here's the integrating factor is I of x for integrating factor. I of x equals, it's kind of a strange looking deal. It's e raised to a power, and the power is going to be the integral of p of x dx. Saying, okay, that's interesting. And you know, the book goes through why that would be the integrating factor. But right now, let's just get used to doing these. And the reason we do that integrating factor is because that is this part of the solutions here. So and then the solutions. So I didn't really talk about it. So yeah, you just integrate p of x, so whatever this is times the y, you integrate it and then put it to the e to that power, okay? And then the solutions are, so the solutions to this differential equation in this proper form here are y equals 1 over I of x, so then we do kind of a reciprocal thing for the I of x, times then the integral of I of x, so it appears in two places, so that's a kind of important factor because it appears in two places. It's the integral of I of x times q of x. Okay, so yeah, it's a little bit of a process. You got actually wind up doing two different integrals, one for the integrating factor and then another integral put together like this. So let's another formula for your formula card, right? Or two more formulas for the formula. All right, so let's do one here. let's solve y prime plus 3x squared y equals 6x squared. And I guess the first thing is to verify what we've got here. We know about separable equations. We're not going to be able to separate this one, but it is in the form of a linear differential equation, isn't it? Because I've got y prime, I've got y, then I've got a p of x, and then I've got a q of x over here. Yeah, this is a linear differential equation. Well, how do you solve linear differential equations? It's basically a two-step process. Go through here, find your I of x, and then plug it into the solution formula here. So what is I of x here? Well, I of x is e to the integral of p of x dx. And so that would be e the integral of 3x squared dx. You know, depending on the type of integral you have, this could be, some are more fun than others. But in this case, what do we got? E, that's a pretty easy one. 1/3 x cubed, so it'd be 3 times 1/3 x cubed. Oh, and then the other, since this is kind of the first integral we're doing, we can just reserve the plus c part of this, the constant part of this, till we'll put it on this one. It is an indefinite, but we're just going to first choose c to be 0, and then we'll take care of the constant at the end. So 1/3 x cubed, and then the 3's cancel out, so we have e to the x cubed is our I of x. All right, so far so good? All right, now step 2, so that's step 1. Step 2 here is then take that and plug the I of x into our solution formula. It's 1 over I of x times the integral of I of x times q of x dx. All right, so we've got the I of x, so it's 1 over e to the x cubed times in the integral, again, I of x, so e to the x cubed again, times q of x, so go back to the original equation, 6x squared. Aha. And so then it's just a matter of solving that integral there. Sometimes there's some simplification you can do, not a whole lot as far as simplifying. Sometimes things cancel, but not in this case. Now also, this, typically, because of the way these things work, I would probably just leave that as is, and then we'll deal with that in just a moment. All right, so how do we do this this little integral here? Well, the first thing we always try, u substitution. This is u substitution, isn't it? If we let u be that power right there, x cubed of the e, then du is 3x squared dx, so du divided by 3x squared. d over 3x squared will be my replacement for dx, so I have e to the u times 6x squared dx is du over 3x squared. And so nicely, the x squareds cancel, the 3 goes into the 6, so I have 2. So now look what I have, 2e to the u du, very simple antiderivative. 2e to the u, derivative would be 2e to the u. And then, like I said, this is where we'll put in the constant. So we'll call it plus c right there. And then, of course, we're going to go back to our x's. So it's 1 over e to the x cubed times 2e, and then u was x cubed, so we got e to the x cubed again, plus c. Okay? Yeah, so that's why I was saying, usually you want to leave this 1 over e to the x cubed as 1 over e to the x cubed instead of making it a negative. Because when I go ahead and distribute that in, we can simplify this, if you will, and get the solution. So we'll have 1 over e to the x cubed times 2 e to the x cubed plus 1 over e to the x cubed times c. And yeah, that's the e to the x cubed will cancel there. So it'll just be 2 for the first part, and then c over e to the x cubed, or c e to the minus x cubed, however you want to write that. But let's just go. Let's just go with that. Let's go ahead. Yeah. So either one of those, perfectly fine. All right. All right, now, we didn't, like I said, we didn't go through why this formula right here, why this formula here works. So let me just verify that this is a solution to our linear differential equation. And yeah, again, note this is a family of solutions because the c can be any number. And so, yeah, we've got a whole bunch of infinitely many solutions there. But let's verify that it does work in this, just to kind of prove to ourselves that, hey, this is a process that's going to work. Find these solutions, all right? So again, remember verifying it, you just plug in the y and the derivative here. So what is the derivative? Well, derivative here would be 0. Derivative of that, just a little chain rule thing. It'd be c e to the minus x squared, x cubed, e to the power, just e to the power for derivative. Times, though, by chain rule, we got to do the times by the power derivative, so that would be 3x squared minus 3x squared. So that's, how are we going to write that? Just minus 3c x squared e to the minus x cubed, something like that. That's my derivative. So let's plug that in. So here's the original equation. So I want to verify that these are solutions, so I'm going to plug in the y to be that, and then the y prime to be that. So let's see. That's a minus 3c x squared e to the minus x cubed plus 3x squared times y. So y is, let's do that one, 2 plus c e to the minus x cubed. So, all that, does that come out to be 6x squared? Let's hope so. All right, so looking at that left side here, how would I? All right, so there's our 6x squared. Let's distribute that, 3cx squared e to the minus x cubed, plus, distribute that to be 6x squared, plus 3x squared c e to the minus x cubed. Hey. How about that? Those are just going to cancel out. They're the same, except one's a plus, one's a minus. Okay. So sure enough, this process works on this one and on the other one. So hopefully we feel more comfortable with it now. All right. Any questions on that? So far, so good? All right. Well, let's see what else we can get ourselves into here. How about, let's solve xy prime minus 3xy equals x squared. We said it's a two-step process. However, there might be a step 0, I guess we might call it, because for that formula to work, the I of x and then the solution formula to work, it's got to be in the standard form. I don't want to just jump in here and say, well, that's p of x and that's q of x, because this one isn't standard form. So, so be sure what you're starting with here is in standard form. This one, again, is not in standard form because of this, this little x here. That y prime needs to be coefficient 1. Nothing multiplied in front there. So, so we're just going to divide, divide by the x, both sides. That'll make that 1y prime minus, divide that by x, be 3y. And then divide that by x, you got x. Now we're in standard form. I've got the p of x is -3, and then this is the q of x. Q of x is just x. So now I'm good to go. I of x is next. I of x is e to the integral of p of x dx. So that's e integral -3 dx. And so that's, again, easy one. We'll do, I think the next one has a little more complicated integral, but most of these shouldn't be too challenging on the antiderivative. That's just -3x. And like I said, we'll continue with the plus c in the next step here. All right. So now we go to the solution formula for linear. That is 1 over I of x. Matter of fact, let's go over here. All right. So our solutions will be y equals 1 over I of x times the integral of I of x times q of x dx. So we've got our I of x, we've got our q of x, so we're good to go. We got y equals 1 over I of x e to the -3x, times then this integral of I of x, which is e to the -3x, times q of x. So we got it labeled here, q of x is just x. Oh, okay. Yeah, and so this one's where I was thinking we had one where it was a little more complicated antiderivative, and here it is. The u substitution wouldn't work on this integral, because of the integral power there, e to the power of the e. This one, if you recall back, the one we did, the technique we used on one like this, I don't know if we did exactly this one, but very similar one, is by parts. So maybe you'll run into some parts integrals on these. So yeah, integration by parts, nothing else that serves as a little refresher on how to do parts. It's been a while. All right, so in parts, remember you need to assign one part is u, another part is dv, and then remember, usually what you want for u is something where the derivative devolves, I guess, or becomes an easier expression. Well, if we choose u to be e to the -3x, that's just going to cycle. The derivative is going to have e to the -3x, so that's not going to cause u to go to a simpler form. Yeah, so let's just call u the x, because the derivative of that is just 1 dx. All right, and so then these two would be the dv, so it'd be e to the -3x dx. believe it's the way we want to go. All right, so du is just 1 times dx. Remember that's just 1, so du is 1 dx, just dx. And then remember over here we integrate, so that'll give us v equals. All right, so now this couldn't be done by parts, but this couldn't be done by u substitution. But this can. The u, let's do it here. U is minus 3x for u substitution now, not this u. You know. All right, then du for that would be negative 3 dx, so divide by negative 3. Yeah, that's going to turn out well. It's e to the u times du over negative 3 then. So that's a easy enough integral. It's negative 1/3 e to the u. And again, plus c, but we'll do the plus c very, very end. So it's negative 1/3 e to the negative 3x. All right, so I think so all that to do our integration by parts. All right, so we're integrating this. So we said we're going to do it by integration by parts. And so it's u v minus the integral of v du, just to remind us of that formula. Integration by parts is u v minus integral v du. So let's see what we got. U is x. V is negative 1/3 e to the minus 3x minus the integral of v, so it's again minus 1/3 e to the minus 3x du. It's du. Well, du is dx. Nicely. All right. So we're almost there. We just got one more integral to do here. The minus 1/3 e to the minus 3x. Well, let's go ahead. That's going to make that a positive there. So let's make this minus 1/3 x e to the minus 3x. Plus, all right, well, again, that's an easy enough integral. We've got basically again, the e to the negative 3x again. We got 1/3 times that. So again, it's just another u substitution. So du again is minus, d over minus 3 is my dx. So you're going to have 1/3 times the integral of e to the u du over negative 3 again. And so, now enough space, so let's do it right here. Y equals 1 over e to the minus 3x times negative 1/3 e x times e to the minus 3x plus, all right, so I've got a 1/3 times a negative 1/3, so it'll be a negative 1/9. E to the u is just e to the u, but again, u is negative 3x, so that'd be minus 3x, and then plus a c. Finally, since we're at the very end of our integration here, that's where we put the plus c. That's a pretty good answer, but as you can see here, if I distribute this, nice things are going to happen, because if I multiply by that, that's just going to give you a negative 1/3 x, because the e to the minus 3x is canceled, minus a 1/9, and again, this times this, e to the minus 3x is canceled, so it's just minus 1/9, isn't it? And then c times c over e to the minus 3x, well, you know, that's really the only thing there that we can clean up. mean, that's fine, but e to the minus 3x is e to the 3x, so let's just write this c e to the 3x. Okay. That was a long one. All right. Did I do that right? Look okay? Okay. Show you one more. We'll call it a day here. Any questions on that? Look okay? So far, so good? All right. All right, let's solve xy prime plus y equals x squared, and we'll say x greater than 0, with initial condition y of 1 equals 3. All right, so yeah, we talked about earlier these initial conditions, and so this one, same idea. What this allows us to do, remember what this allows me to do, most of our solutions come out with a c constant there, which means c could be anything, any number, but when we have an initial condition, that'll enable us to find a specific specific c value. So just one more step added on to this. All right, so let's see what we get ourselves into. So again, not in standard form because we got that x in front. So let's divide through by x again. So it'll give me y prime plus y over x, but let's write that as 1 over x times y, because that 1 over x will be our p of x equals x again. That'll be our q of x. So this is our p of x, and that's our q of x. All right. So it is linear differential equation. So the way we're doing it is we're getting this integrating factor I of x, which is e to the integral p of x dx, which is, in this case, e integral. Oh yeah, this is something else that can happen. Yeah, this, of course, the integral of 1 over x dx is what we're integrating here. Well, 1 over x that's our ln, is ln of the absolute value of x. However, we put this x must be greater than 0 on it, and so the absolute values there are not necessary because it is already greater than 0. So it's e to the ln of x. However, there's more here because, yeah, we've got these e to an ln, and those are inverse operations, if you will. Those just cancel out. And so this one nicely, we got that happening. The I of x is just x. So we don't even have e involved in this one as far as the I of x is concerned. Is that okay? All right, so now we go to our solution formula, which is 1 over I of x times the integral of I of x times q of x. Oh yeah, this one's going to work out so very nicely here because this becomes 1 over, well, I of x is x, so it's 1 over x, times the integral I of x, well, I of x is just x, and q of x is also just x. Move over here a little more space. And so y would equal 1 over x times the integral of x squared dx. So that is 1 over x. Simple integral. We run into those every once in a while. It'll be nice to us. And give us a simple one every once in a while, maybe. 1 over be 1/3 x cubed. And again, this is where we put the plus c because we're our final integral here. Let's see, distribute the 1 over x. Does that do anything for us? Yeah. So I do 1 over x times the 1/3 x cubed, and then the 1 over x times c. Yeah, that does. That x cancels into the x cubed and leaves me an x squared. So it's 1/3 x squared plus c over x. Right, that way. However, we can't stop because we've got this initial condition. Initial conditions means one more step on this. And remember, what we're going to do is figure out what the c specifically is, because we've got an x and a y value that we can plug in here. X is the 1, y is 3. Plug those in, we can figure out c. Let's do that. Y is 3, x is 1. Oh. Obvious there, okay. So what do we got? 3 equals 1/3 plus c. All right, so 3 minus 1/3 is what c is, and so I think that would mean c is 8/3 or 2 2/3, something like that. 9 over 3 minus 1 over 3. Yeah, and so our c is 1/3, so our solutions are y equals 1/3